Thank you very much for coming and connecting. It's my first time here in Noir Lab and in Arizona in particular, and it's very nice to visit. And I'm going to tell you a bit about an ongoing project at the Center for Decoding the Universe at Stanford University, where we're attempting to build a unified observational picture of nearby galaxies across wavelength and scale. The image I chose to present here is of one of these galaxies that we're trying to model. This is specifically NGC 628, where the top left triangle is a color composite from the Hubble Space Telescope, and the bottom right part is a color composite from the James Webb Space Telescope. And I've been told that the audience is quite diverse, so I will start with a couple of things that I think describe astronomy and astrophysics. I'm an observational astronomer in my training, and what we're trying to do as astronomers and astrophysicists is to observe and understand the universe, including everything that's inside the universe: stars, galaxies, planets, black holes, and the gas that connects it all that we call the cosmic web. We're trying to answer questions such as what is the universe made of, how does the universe work and evolve, and what are the physical laws that drive the formation and evolution of astronomical objects and the universe as a whole system. And what makes our field special compared to other exact sciences is that we cannot really build an experiment in the laboratory. For example, I'm interested in galaxies, and unfortunately, I cannot build an experiment where I can track how a galaxy forms and evolves on Earth. But instead, what we do is that we use the night sky and the billions of astronomical sources we have in the night sky, which are all essentially an ongoing experiment. And under the assumption that the physical laws should be the same regardless of the system that we look at, then all of these systems have different initial conditions perhaps, but their evolution is governed by the same physical laws. And astrophysics is a subfield of physics, and there are fundamental physics that are only accessible or mostly accessible through astrophysics research, such as the general relativity, dark matter, dark energy, and extreme matters of state, so temperature, energies, pressures, etc., etc. And so it is interesting to study astronomical sources, both in the context of understanding physics better. And as I said, our way to study the universe is by observing astronomical sources. And we have been extremely efficient as a community in doing so. And the next decade shows that even more. I'm showing here only 4 upcoming or ongoing missions or surveys that I'm particularly very excited about. We have the Rubin Observatory, which is going to obtain images in 6 different optical bands of around 20 billion galaxies. We have DESI, which is ongoing, and it will obtain around 30 million galaxy spectra across the optical wavelength range. We have Euclid, that is going to obtain around 1.5 billion galaxy images, both in visible, so optical, and in near infrared, and tens of millions of low resolution infrared spectra. And our eyes are of course, set forward to Roman, which is going to also obtain images of billions of galaxies and spectra, low resolution infrared spectra of millions of galaxies. Now, I am very interested in galaxies in particular, and this is one of the main things that these surveys are going to observe. Not the only thing, but one of them. And so galaxies are one of the main astronomical sources we observe, and they're an ecosystem composed of millions to billions of stars, planets, gas, dust, dark matter, black holes, and all of these things are bounded together by gravity. And when we look at galaxies and we check the intensity or the radiation of photons as a function of their wavelength, we essentially see that galaxies emit throughout the electromagnetic spectrum. And this emission traces the different objects the galaxy is composed of. Stars, gas, dust, black holes. And the thing to note is that these objects evolve not in vacuum, but by interacting through different physical laws, one with the other. And these interactions leave complex and overlapping fingerprints on the emission that we see from a galaxy. So there is no wavelength that is sort of tracing a single component in a galaxy, but rather a mix of the interaction between these different components. And our challenge as astronomers is to observe galaxies and to tease these different fingerprints out and constrain the physical laws that drive this coevolution between all of these things. And this effort obviously benefits from combining data from multiple surveys across different wavelengths, because then we have more constraining points essentially on the theories that we're trying to build. Now, I think that an extreme case of what I described now is the case of the very nearby universe. So galaxies at distances of 20 megaparsec and below from us. These are very close, very big galaxies on the sky. They usually have names, NGC and a certain number. And I'm showing you one of these galaxies here. And the exciting or cool thing, and this is why I think that this is essentially pushes our challenge of combining observations across multiple surveys, it really pushes it to the limits. Because these galaxies have essentially been observed by almost every telescope and instrument that astronomers have built. What you can see here again, this is emission. This is radiation or intensity as a function of wavelength. I'm showing here around 7 orders of magnitude of wavelengths. And here at the top, I'm showing you images of the same galaxy obtained at different wavelengths through narrowband or broadband filters. These filters record the emission coming at around the wavelength that we're talking about, and we get a single channel image of this galaxy at these different wavelengths, as you can see here. So we have emission from the far ultraviolet here through the optical, near infrared, mid-infrared, and far infrared here. But in addition to these images, we actually also have spectral cubes. So spectral cubes are observations in which I essentially get these types of images, but at a very dense sampling in wavelength, essentially. And so in every little pixel here in the galaxy, I essentially get a full optical spectrum that contains both a continuum emission and the spikes that you're seeing here coming from transitions of gas in the galaxy. So we have this type of spectral cubes both in this area here, the optical wavelength range, and in the mid-infrared wavelength range by Spitzer, which is an old-generation telescope. And to add to that, we also have interferometric cubes in the millimeter and radio wavelengths, tracing specific transitions that one of them is associated with cold molecular gas in the galaxy, and the other is associated with neutral hydrogen in the galaxy. And again, every point here has a spectrum with this emission line, essentially. And so the dream or the hope is that we can take all of these observations together to inform the models that we're building about galaxies and about how stars form and how they exert different types of feedback processes on the gas around them. But in principle, it is very, very difficult. Why is that? First of all, each of these different images that you're seeing here has been obtained by a different instrument and a different telescope. And there is a complex and individual imaging process that takes place when we're obtaining these images. So each of these instruments has different resolutions, noise properties, artifacts, and some of these things are known only to a certain degree. So some of these things we know well and characterize well, but others not so much. If the telescope is also on the ground, so not on space, we also have the imprint of the atmosphere on the light that comes to us. And this is also something that has to be taken into account. And so in the image that you're seeing here, this is the same region in the sky observed on the left with the Spitzer Space Telescope, that's the older generation mid-infrared telescope we had, and the James Webb Space Telescope on the right. And so you can see the same type of sources are sort of observed in both, but the shape of these sources is different, and this is because of the point spread function. This is essentially what happens to point sources as they move through the telescope onto the CCDs that we're working with. But in addition, the noise properties, the depth are obviously different. And so here now, for all the space telescopes here, I'm showing you the point spread function shape. So you can see that the shape itself is different from one telescope to another, but another thing that is different is the actual angular resolution at which we can obtain these observations. In these gray boxes, I'm showing the angular resolution of the maps that we're having here, translated also to the spatial resolution at the distance of this particular galaxy. And so you can see that while in some of the cases, we have superb spatial resolutions, for example, with the Hubble Space Telescope and the James Webb Space Telescope, if we're, for example, looking at the older generation telescopes, the resolution can be 5 to 10, even more, like even up to 50 times worse, essentially. And you can see it in the image, right? I mean, you can look at this image and you can see how much structure we can identify around the spiral arms of this galaxy, whereas if we look at the Herschel image, this is all kind of blurred, essentially. And so what do astronomers typically do? If we want to make an inference that uses several of these products together, the first thing that we would like to do is to degrade the high resolution observations to the lowest resolution observations that we're considering, because we want at the end of the day to compare apples to apples or to trace the same scales consistently across these different wavelengths. And so, for example, if I would like to have an inference that uses far ultraviolet observations as well as optical and infrared observations, I will have to take these beautiful images and I will have to convolve them and degrade their resolution to this resolution, essentially, losing a lot of information in the process. And because of this challenging trade-off, we will usually prefer to exclude completely images taken by older generation surveys and instruments, because we do not want to degrade the resolution so much. And so, for example, my inference using UV to mid-infrared images, for example, will not benefit from the additional information I can get from far infrared wavelengths. And so in practice, because of that, we typically do not use more than 10% of all of these available data when we do our inference, because of this degradation of resolution. And to bring this point home, I want to show you the Phalanx galaxies. These are these very nearby galaxies, and what their images look like in our press release papers, versus how the same galaxies look like in actual scientific papers analyzing the same galaxies. So you can immediately see the degradation and additional things that we're not still able to take care of. So for example, one of them are these point spread function imprints on the center of the galaxy. We have all of these, you can see here, all sorts of different artifacts that we can see in these images. And so even with our best instrument and the best telescope, this is the type of science we can do. And we want to see whether we're able to extract more from this data. So this is the goal of the big project that I'm going to present here. It is still very much work in progress. I will describe where we are and what we're doing. But essentially what we're trying to do is to observe galaxies as a sort of inverse problem. where we are building a probabilistic model of emission, both in space and in wavelength. And we're building a forward model to the actual observing space that we're seeing here on the right. The three main people at Stanford, besides me, that are working on this are these people that you're seeing here, but there are a couple of additional people that are being involved, and so on the left here, what we're doing, we essentially want to build a probabilistic model of emission, both in two spatial dimensions, X and Y, and in the wavelength dimension as well. So for the spatial fluctuations, we're using hierarchical Gaussian processes to define a distribution over the emission field. And essentially, you can think about this as like we're learning and fitting the power spectrum of fluctuation of radiation at every wavelength. And the spectral part is encoded using spectral components where we learn the correlations between them. Now, because this thing is probabilistic, we're getting a posterior distribution over the emission. And then we take this thing and we model everything that we know to the extent we know it. So we're modeling instrument-specific and sky-forward models, where essentially every galaxy is modulated by the distance of this galaxy from Earth, then by what happens to photons as they move through the atmosphere, what happens as they move through the telescope and the instrument, so the point spread function, the resolution, the noise, and we're also trying to model the survey strategy, things like the mosaicing, cross-calibration between these different images. So we're trying to model everything we know, and an important point perhaps to mention is that we do not know these things 100%. We know them to a certain degree, but we're building models that do depend on a number of parameters that we're fitting during the fit of the entire thing. And at the end of the day, we're essentially measuring or projecting it on all the observables that we have, the images, the spectral cubes, and we're fitting it to obtain this probabilistic. So I'll describe the two most advanced projects under FM-ISM. This thing, we call it at the moment FM-ISM. And there are two sub-projects that are currently in quite an advanced stage. The first one is led by Stephen. This is astroprism, where he's combining photometry from different space telescopes. He's using 31 photometric bands spanning from the far ultraviolet to the far infrared. And because we're only modeling images, so photometry, not any spectral cubes, we're actually treating each band as a separate feature, and we're learning the correlation, the spatial spectral correlation between them. We model the point spread function. We model additional blurring that is introduced by dithering of these surveys, and we model instrumental noise. Here you can see these are all the images of the galaxy that we're modeling simultaneously, ordered by the wavelength of the filter from the far ultraviolet here all the way to the far infrared here. And some of the degradation that you're seeing in these wavelengths here is driven by the resolution of the observations, not by different spatial structures that you see in different wavelengths. But this is something that we're essentially trying to forward model. And one of the type of tests that we're doing to understand how well we're able to recover the spatial structures of these galaxies and to which scale we're able to do it accurately enough to do scientific inference, we take some of these images and we mask out half of them, the bottom half of them, and we run the entire fit essentially, and we get a posterior prediction of what the emission in the bottom half looks like. So this is what you're seeing here at the bottom row here, and you can compare it to the actual ground truth, the part that we actually masked out. So things are working pretty well. The reason why they're working is that though these are the bands that I masked out, I still have more than 20 bands where this region has not been masked out. And if the images show significant correlations between these different bands, we do have enough of information to reconstruct it. And we can actually push and check at which scale, as we move to smaller and smaller scales, our accuracy in being able to reconstruct things will be degraded. And so we can start asking the question of when exactly it happens and to which extent we're able to use it to do inference. Now, what's the goal? My goal, what I hope to be able to do, is to do a truly multi-wavelength inference using all of these filters together without degrading the resolution. So I'm not interested in building high super resolution maps of images where I don't have this resolution. This is not something I'm interested in. What I'm interested in is to use the native resolution of each of these wavelengths to do my inference without the degradation. And this is something we can do thanks to variational inference, where essentially the posteriors that we obtain are posteriors that we can take derivatives of and we can integrate over, which means that we can build inference tasks on these observations. And this allows us to essentially build all sorts of questions that require us measuring the entire wavelength range or using the entire wavelength range. One of them, for example, is constraining the dust composition and extinction curve on around 100 parsec scale using data from far ultraviolet all the way to the far infrared. Those of you who are familiar with dust know that dust absorbs radiation in these wavelength range in the wavelength dependent manner, and then dust emits radiation in these wavelength ranges, depending both on the absorbed radiation and on the properties of the dust. And so in order to understand what dust is doing, we really need a wide wavelength coverage. And what I really want to do is to get more empirical constraints on the spectral shape of the interstellar radiation field, which is obviously tied together to the dust extinction, and hence constrain radiation from stellar populations, from the data itself. So I'll just note that we are very close to done. Stephen has written a beautiful package to do this type of fit for any type of arbitrary set of instruments and telescopes, and he will release it for public use once it is done. And the tests show that we're getting quite close to being able to trust the model that we're building in order to do inference. The next project is Sonia's project. And she's working on building a Spitzer JWST synergy. And I call it combining all the new to approach the unattainable. And I will explain in a second what I mean by unattainable, what exactly is unattainable. So we have an old and a new telescope covering the same wavelengths. We have the Spitzer Space Telescope that provided us with spectral cubes. So we have actual spectroscopy in the mid-infrared, but at relatively coarse resolution, so 500 parsec. And we have the James Webb Space Telescope that only provides us with photometric images and these wavelengths that you're seeing here, but at a superb resolution of 10 parsec. You can see here images of relatively close wavelengths of the same galaxy from these different telescopes. And why do I call it unattainable? So this image is a bit scary, so let's unpack it slowly. The grayscale background that you're seeing is one of these images in mid-infrared wavelengths by the James Webb Space Telescope. All of these boxes that you're seeing here, these are all the different spectroscopic cubes that Spitzer has obtained for this galaxy. So there are, I don't remember how many in this particular galaxy, but in the different galaxies that we examine in this project, there are between 10 to even 30 such cubes, essentially. And each of these is essentially the footprint. The resolution is not great, but this is spectroscopy that we do not have with JWST. Here is, for example, one such stitched spectrum that Sonia made from one of these cubes. And why is it unattainable to build spectroscopic cubes otherwise? So in principle, like the best thing we could have done is to actually obtain spectroscopic cubes with the James Webb Space Telescope. The problem is that the field of view or the footprint of the IFU on the James Webb Space Telescope is tiny. And so we do not have any way of covering these galaxies entirely. We cannot get spectroscopy of everything. And so getting full spectroscopic cubes at the JWST resolution and quality is an unattainable task. What we can do is to use this information, spectral information that we do have, plus the superb spatial information that we have from JWST to reconstruct cubes, again, with assigned uncertainties and scatters that are defined by the uncertainties of what we can and cannot observe. Coming very soon is actually starting to fold in JWST spectroscopy that also starts to flow in. This is, for example, from the M51 Treasury program. And you can sort of compare the quality of this spectrum to the quality of the Spitzer spectrum here. So even if you have tiny little boxes scattered around each of these galaxies, a number of them, it already gives us extra information that we can fold into the model to build a more precise spectral cubes of these galaxies. So what Sonia is doing, the type of forward model that she's building, is that she first generates spectral cubes using the same type of Gaussian, hierarchical Gaussian process, plus spectral components that are added together in order to represent the spectrum in every point in the galaxy. And then she does the Spitzer and JWST imaging process. So she takes this generated cube, she applies the point spread function, the spatial sampling, the noise, spectral resolution. In the case of the JWST, here you can see, for example, this is a spectrum that is reconstructed by her method. And then she takes the response curves of the JWST filters here, integrates under them to generate what would the JWST images look like, essentially. We still have some interesting artifacts that we are dealing with in the JWST images, but we're moving along. And one of the reasons I'm very excited about this project is that it will enable us to map the properties of small carbonaceous grains that are called PAHs, much better than we could do only with JWST imaging. So JWST imaging already has revolutionized completely our understanding of how these small grains are distributed across the interstellar medium. But one of the main difficulties is that these are emission features coming from these grains. But the problem is that there is a sort of underlying continuum that it is quite challenging to subtract without actual spectroscopy. And so one of the reasons I'm very excited is that I think we will be able to map the emission features of these small grains much better. And these small grains are extremely important in the context of heating and cooling in the multiphase interstellar medium. And they're also sensitive tracers of the spectral shape of the radiation fields of stars. So I'm very interested in the spectral shape of radiation fields of stars, and I think that we might be able to get new constraints on that through this. We have two newer, less mature projects. One of them is attempting to combine the Muse optical spectroscopy with the HST photometry, so essentially combine spectral cubes and images here. The reason it is more complicated than what I described with Sonia's project is that this data is obtained by a ground-based telescope. And so the radiation goes through the atmosphere, and the atmosphere imprints various absorption and emission features on the spectrum, which surveys try to correct for and account for imperfectly. So what we're trying to model is not the actual sky imprint, but the sky imprint after the survey tried to correct for it, which I'm very happy to go into more details about it because we have been battling with this for a while. But this is, we are making progress there. And another one is starting to fold in the interferometric observations and starting by combining them with the JWST imaging. These are two additional rotation projects taking place at Stanford. Now, what do we want to do with FM-ISM, the entire thing? Once hopefully we're able to build the entire thing and fit all the galaxies in a constrained fit together, what do we want to do? So the first thing is enable inference using all the data without degrading the high resolution observation. This can be done by sampling from the posterior and building the inference directly on this posterior. And in such case, so essentially like what we're trying to do is to reconstruct this gray line that you're seeing here. And what the Gaussian process, the entire probabilistic treatment that we're doing should give us, it should give us an uncertainty bound around this gray line that we're trying to reconstruct. So in places where we have constraints, we will have small uncertainties, but in places where we don't have constraints, for example, here, or on spatial scales in which we do not measure things very accurately, we will have a larger uncertainty. And this is something that is going to be propagated in the inference that we're doing. I'm also very interested in applications of data science tools to astronomical data. And I've been dreaming of something that will combine like a giant interpolator between all the different wavelengths so that we can start doing data-driven science with all the data. And the last thing is that we're going to build this Gaussian process model, and it's going to be represented in a sort of latent space, which we hope to be able to explore with the goal of uncovering the correlation structure imprinted on these different observables by the physical processes connecting stars, gas, black holes, dust, etc., etc. And perhaps this type of model can be used as a basis for connecting multi-wavelength observations of billions of galaxies using something like an astronomical foundation model. So Francois Lanous gave a seminar here, I think a couple of weeks ago, describing astro foundation models, this idea of building a model that is not tuned for a specific task of classification or regression, but sort of learns what are astronomical observations in general. And there are a couple of these foundation models that are being presented around. And I think that one of the main things many of them have in common is they're essentially training on both images, spectroscopy, some other physically derived parameters, but they do not actually model the imaging process by the different telescopes. And so, for example, they model galaxy images without taking into account that the point spread function or the noise characteristics could be different between images coming from different sources. They do not take into account the fact that the spectra they train on are taken through a finite aperture that does not cover the entire galaxy. And I think that we already see some evidence that us not being able to model the imaging process before building a foundation model actually hurts the foundation models that we're building. So for example, this paper here presented the first attempt to build a foundation model using Euclid images, both in near infrared and in visible wavelengths. And they saw something very interesting. Essentially, they built a billion parameter model. And one of the main tasks that these types of models should be able to do really well is morphological classifications of galaxies. This is one of the things, essentially, that deep learning has essentially revolutionized in galaxy science. And the interesting thing that they're observing is that their ability to perform morphological classification actually degrades when they include near-infrared observations. So you're adding information, but your ability to do morphological classification degrades. And I'm thinking it's a symptom of us not modeling the imaging processes of these different telescopes before building a foundation model. And I will just note that other foundation models, like AlphaFold, for example, this is a good example of a foundation model that is built with both of these pieces. So first they have the measurement to the protein structure reconstruction. This is one thing that happens, and only then they're training on and building a foundation model. So perhaps we could use something like FM-ISM to reconstruct the galaxy images before all the effects of the instrument.
But if adding information reduces your ability to discriminate, doesn't that suggest you just have the weighting wrong and use it to reduce the weighting on the infrared images?
That's a good question. So they didn't go into a lot of investigations of why that happens, why the morphological classification gets worse when they're not only using the optical images, but also the near-infrared ones. They do mention that it might be related to the fact that these different cameras have different characteristics and different resolutions.
Or it could just be that they sample the older stellar populations that are much more similar than the younger populations in the ultraviolet. They give you much more discrimination of morphology. And if you weight them right, then looking at Todd, you were probably understanding, I thought if you just get the weighting right, you would. You're not adding much in the infrared, but you shouldn't be losing your discrimination.
I have about a half hour worth of questions.
Uh-oh.
But maybe I shouldn't interrupt you.
But since the basic question that I have, this is a lot of really impressive work to match galaxy images. But you go in knowing an awful lot. I know about stellar populations, I know what dust does, and so on and so forth. And the questions are, when do I need resolution, when do I don't? When can I look at broad features? And it all depends on the scientific question. If I want to know, about dust, I may not need the best resolution. I may be able to understand stellar populations without picking apart individual stars where I'm using the resolution. And so Pat's question goes into this, is what exactly scientifically are you trying to do? And for that particular question, do I really need all this data? Do I need all the resolution? Do I need all the hard work that you're doing? Maybe I can cheat, okay, because I'm lazy. Maybe I've got UBV, and that's all I need to measure the dust. And so, I've got a paper published before you do.
Yes, that's an excellent question. So I think that you could answer many of these questions, at least to a certain degree of accuracy, without building this entire thing. So for example, you could think of a case where you're not degrading all the good resolution images all the way to the Herschel resolution, and instead assume that the Herschel resolution infrared images are sort of like the dust field, the far infrared dust field, in order to constrain the intensity of the radiation field you need in order to constrain the dust extinction curve and its properties, for example. So people do things like this, and they sort of also pick inferences in which you can limit to a certain degree the wavelengths that you're considering at the same time. But I can give you a couple of examples, very concrete examples of things that I wanted to do with the FANGS dataset that I can do much better once such model is actually fitted. So one such example, I am very interested nowadays in these features, in the PAH features, and I'm particularly interested in their flux ratio, so the ratio between different features, because these ratios trace both intrinsic properties of the PAHs, like their ionization and their size distribution, but they're also sensitive to the spectral shape of the radiation field. And I believe that a lot of the variation that we see in their band ratios is actually driven by the changing radiation field. And so being able to understand what is the continuum and how to subtract it out, for example, this is very important to me. What's the continuum of the stars here? What's the continuum of the hot dust grains here? This is something that is very important for me. We're doing what we can with photometry, right? We're drawing lines. We're using like the things that we always do when we're trying to derive line fluxes from broadband photometry. We're doing that. I believe we can do that better if we fold in the actual spatial spectra that constrain this continuum much better. Another thing I'm very interested in, it is this one. It was commented out. Oops. Yeah. Okay. So what you're seeing here, this is an image derived from the Muse observations from the H alpha line. This is a recombination of hydrogen line. And the map that you're seeing here is a map of where we see a significant H alpha emission. This mostly happens in places that we call H2 regions. These are places where young and massive stars have just formed, and they're releasing ionizing radiation that creates these ionization bubbles, essentially. So you see all of these bubbles driven by the young and massive stars. And if you zoom in to one particular case, this is what it looks like. And if we now compare it to the Hubble Space Telescope data that we have both narrowband filters, like the one that you're seeing here, of the H alpha, and you can see the structure. And more interestingly is that we can actually, at the Hubble Space Telescope resolution, we can actually identify star clusters. The same star clusters that presumably should power the radiation that we see in this H alpha nebulae. So we have these beautiful maps from the narrowband H alpha filters from the Hubble Space Telescope. And we try again to subtract continuum as best as possible using the photometry only, the way astronomers have always tried to subtract stellar continuum emission from photometric bands. And the result is that we're losing about 70% of the nebulae that we're detecting here. Now, what if we are going to fold in the Muse spectroscopy and do an inference together? Can we identify more of these H2 regions? Can we dig deeper and basically move forward the detection threshold to lower flux detection thresholds and identify more nebulae using the Hubble Space Telescope observations? So this is another thing I really hope we will be able to achieve. So things where essentially having a spectrum allows you to do the inference from the photometry better.
So
can we?
what you studied?
Do you want to wrap up this and then we finish the talk and then we go back to questions?
Whatever.
No, I mean, please finish your thought on this.
No, we can save it.
No, I meant finish this thought before we start a new one.
Right. So I really appreciate your discussion of this particular problem, because that isolates a scientific problem where you need this information on different scales. And that's why I'm asking the question, is like, as much as I enjoy image processing, and I really do, I really want to say, what's the laziest way I can get after a question? For example, here, you said earlier that it's too bad that, I can't map the galaxy with JWST, but this would be a great justification for saying, I'm going to get the JWST IFU observations of this particular area, and that's all I need. I don't need the whole galaxy. But it raises questions, when you say you need the radiation field, I appreciate that, but then I say, well, gosh, do I really need that high resolution? Can I make an inference over the whole galaxy? And so for that particular problem, I look at this and say, here I want to be very careful, here I don't, here I can use a low resolution. Making a whole galaxy that fits all 31 bands, be frank about, is not something that how I would approach this problem. I would more pick it apart like this.
Yes, that makes total sense. If we are driven by a specific scientific question that we're trying to answer, it is unclear that we would want to build this entire ginormous framework in order to answer the specific scientific question. I do believe that there is a subset of scientific questions we didn't even think about asking because we do not have tools that are able to combine all of that. And as we look forward to combining Rubin with DESI, with Euclid, with Roman, then we really need to get understand better how we want to make this combination, essentially. And so both because of that, and again, I'm interested in things that are related to data-driven discovery, and I want to have access to all of the wavelengths, essentially, to do that. But I agree that for a specific scientific question, it's not clear at all that you need this gigantic thing to make real scientific progress on this question.
I mean, the way I express this for many problems is, do you want to do diamond cutting or strip mining?
Yes. Yes, and I, again, totally agree. Okay, I'll just say one more word and then we will finish. And this is about, I talked a bit again about foundation models and the fact that they're training on spectra without taking into account where these spectra were actually measured from. And I think that this is going to be a very interesting challenge using the DESI spectroscopy because DESI has fibers of 1.5 arc seconds, essentially. And so for many relatively nearby galaxies, they're tracing only a small fraction of the galaxies themselves. And I think that this information, if folded into an inverse galaxy imaging inverse problem, and then into a foundation model, will actually allow us to build stronger foundation models. And just as an example, I'm showing you something that a PhD student, a brilliant PhD student at KaiPAK is calling DESI IFU mode. So in DESI, some galaxies are actually covered by multiple observations. And so you have, again, this poor man IFU of spectroscopy from different regions in these galaxies. And I think that being able to fold such information in before we're thinking about building these big billion parameter models to describe Rubin together with DESI and Euclid, we might want to utilize this type of information to build something that is more substantial about each of these galaxies. And that's it. Thank you very much.